Klee, Irwin, and the research group at the Quantum Gravity Research Institute near Los Angeles. This is Richard Feldman. I've made a dozen or so videos with the idea of trying to show you the work that I've been doing in the development of a language of connectivity called TNNs, Triangular Neighborhood Networks. But before I start, let me say how much I've enjoyed all of the videos that you've produced in the last months. I've looked at all of them, and several of them a couple times actually. In particular, the four that I like the most are the quasi-crystalline video, Is the Reality a Simulation?, the Code Theoretic, and then the Overview. These are all masterful videos, and I've learned quite a lot about what you've been doing. I trained as an electrical engineer, and I've always thought of problems in terms of connectivity. That is to say, originally wires that had signals, electric voltages on them. And so in 1960, when I went to graduate school, I started to play with models of different kinds. And so at that time, I built the platonic solids, and did this in plastic using plastic plexiglass sheets. And so two of the models survive of the five platonic solids from those days. But after building models in plastic, which I can only do so large a model, I started building them in wire. And so I've reconstructed this wire model of an icosahedron just the other day, and had quite a bit of difficulty making the thing, and cut my fingers in doing it, and in general realized once again why it was that I abandoned these wire models after a while, because they just didn't, it wasn't possible to build large models because the lengths of the unit's edges would change from place to place, and you could creep in the model. And so I could only build things a little bit larger than this. But in 1965, I was in Germany, and working with Carl Adam Petrie at the Institute for Instrumentelle Mathematik in Bonn. And he introduced me to the Knupfli elements. Knupflis are plastic edges, graph edges, made by a company called Dusima near Stuttgart. And I wound up buying 50,000 of these elements and started making models. So here's, again, an icosahedron structure made of the so-called Knupfli. Knupfli means, it's a German word, means, Knupf means connector, and Li is the diminutive. So it's a small connector. It's a children's play toy, and the company shows you various very small structures. The structure I just showed you is an open weave, and some of the models, the smaller models, I've built like this. But this is the close weave that I usually use. And you can build models like the icosahedron. So, for example, these two things are equivalent in structure. But of course, I've also built very large models, some of them filling the whole room. So this language in which the triangular neighborhoods are the most common feature are really quite elegant. And the videos that I've made try to show you the different structures and properties that I've found. I hope that you would look at them. But let me just tell you something about myself. As I say, I trained as an electrical engineer, and eventually wound up going to the NIH in Bethesda, Maryland, where I stayed for 29 years. During that time, I was mostly concerned with proteins and DNA and RNA, the structure and nature of these atoms and molecules. But if you think, if I want to tell you who I am, if you've seen the surfaces of atoms as spheres, either proteins or DNA or RNA. Well, I was the first one to do that. And of course, this has been extremely popular and is commonly used. You can look in any issue of Nature or Science and at the protein structure papers, and there most probably will be an image in the style that I developed in 1976. I did that project with Tom Porter. Tom was at the NIH at the time, and eventually he left and went to Pixar, where he's done animation. Tom got 5 Academy Awards for his animation work. And then I've also made movies of proteins. In particular, I made 2 movies for Michael Levitt, Martin Karplus, and then also as a collaborator, Ari Washel. Those 3, a couple of years ago, won the Nobel Prize for chemistry, all 3. So I had the distinct pleasure of having 3 Nobel Prize winners as collaborators from 40 years ago. So as I mentioned, I have a long-standing interest in self-defining, self-developing systems. I developed a language for surfaces, the triangular neighborhood networks, and these surfaces are capable of recursion. And this is a very important property, and I'll spend quite a bit of time in one of the videos telling you more about that. The Knupfli plastic elements are really a rapid prototyping tool. And this is the main way in which I use them. It's possible to have an idea, build a model, perfect the symmetries in the model, and get the model to close, and then go on to put the model into the computer. It turns out that putting the model into the computer is very much more difficult, and that can take days, to do. And yet I've done this for a number of different features. One of the things that I've found and feel is that these triangular neighborhood networks are have a very simple syntax, and are very easy to apply in a number of different topological configurations. I think, and I have thought for a long time, of these triangular neighborhood networks as particles and fields. And so I have in these videos demonstrations of these various properties. My fondest hope would be that eventually I or we could show that a particle is really an organization of topological features, and that these organizations change in time in certain well-defined ways. The reason for making these videos is that I would like, first of all, to bring to your attention the work that I've been doing and the enjoyment that it might possibly give you. But I also hope that it might be possible to form a relationship between the E8 space groups that you're working on and these triangular neighborhood networks. And if we could do that, I think we both would be excited and happy about that. Just a small comment. This video and the ones that follow may not be up to Hollywood standards. I'm just doing this for the first time, and so as I make the videos, there are mistakes in what I say, and sometimes I drop the objects. My hope is that the ideas will come across, and if it turns out that the video quality is really a problem, well then please let me know, and I'll try to do something about that. But in the absence of that sort of comment, I'd prefer to just have the models and the ideas speak for themselves. After looking at the videos from the Quantum Gravity Research Institute, I realized that many of you are really keen on shirts, t-shirts. And so I've taken this idea from you and have made a t-shirt for myself describing what I believe. So let me just push the camera like this and show you my shirt. Unfortunately, the Logitech camera reverses left to right, and so you can't read this. I'll print it and then take a photograph of it. This is the printout of the axiom that's on my t-shirt. It says that toroidal holes can neither be created nor destroyed. This axiom is important when one goes from one level of structure in the triangular neighborhood network model to another level of structure. As this happens, each edge is replaced by a pipe, and the pipe itself is made of triangular neighborhoods. These triangular neighborhoods themselves can be represented at the next level by toroidal holes. And so as one goes down from one level to the next in the recursive model of the triangular neighborhood networks, the number of triangular neighborhoods, and hence at a lower level the number of toroidal holes, must be conserved. Edge rotation, of course, does exactly that, because the number of triangular neighborhoods, and hence the number of, at a lower level, the number of toroidal holes, is conserved. And this turns out to be very important in building the model of the triangular neighborhood networks. One of the things you might be wondering about is, what is this painting here on my behind me on the wall? Well, in 1967, when I went to the NIH, I was staying in a rooming house in Silver Spring while our house here in Durwood was being built. It took 6 months to build the house. So during the time I was in this rooming house, I had the idea of making a painting. And so I collected the fiberboard and the acrylic paints, and I painted the one painting that I was interested in making, and that was a sun. And so I painted this painting, and the sun just about fits into the frame. And this was my view of the universe, of my life in 1967. And today, it's still my view of the world. I view the world as something magnificent and just bursting out at us. And so I thought you might be interested in knowing a little bit about the history of this. What follows is a playlist of the videos that I've made. It turned out that there are quite a number of subjects that I have to bring to your attention before you would have a complete understanding of my view of the world and how a system of connectivity might build itself. Obviously, the goal is to provide a uniform syntax in which a system could construct itself. My view, of course, is that this is essentially a topological process, and the triangular neighborhood networks provide the simplest syntax for self-construction of a system of arbitrarily large extent and complexity. And so I've been forced, in a certain sense, to develop these individual aspects of topology and in the triangular neighborhood network syntax. And so you just have to go through these videos before you will have a complete sense of the range of possibilities of the triangular neighborhood syntax in terms of its generation of topological properties. And then the last video is a summary in which I try to bring together all of the ideas and convince you that this is something that is interesting. In the end, there are 15 videos that take altogether about 6 hours. I've listed the times for each video on the left. The first video is an introduction. That's this video. The second one is on growing triangular neighborhood networks. The third is on scaling the ground state and pipes. Fourth is on grammar, curvature, and toroidal objects. The fifth is on recursion. Sixth is on signal flow. Seventh is defect propagation. 8 is the change of levels of toroidal holes between one level and another. 9 is the melting of an icosahedron. 10 is the idea of particles and antiparticles. 11 is interaction of different pipes. 12 is the structure of various fields. 13 is a discussion of gravity. 14 is a discussion of the Big Bang. And 15 is the summary.